All right, Unit 5 was implicit derivatives and related rates. I don't have much on this unit because, most of the questions involved just practicing and they were long questions. But we had these implicit curves that we needed to find the derivative of. We're taking the derivative with respect to x. One thing we need to remember is that whenever we're taking the derivative with respect to x of a y, that because of the chain rule, you need a dy dx after it. So I get 2y dy dx. So as you're taking the derivative of x squared, 2x, then the minus. Be careful with this minus. You can either bake it in or leave it out, but just don't forget to distribute it. I'm going to bake it in so I have a product. Make sure we use the product rule. Derivative of negative 2x is negative 2 times y. Derivative of the first times the second plus the derivative of the second. The derivative of y we say is dy dx times the first, which is negative 2x. Plus the derivative of y squared, 2y dy dx. And then the derivative of 4 is 0. Okay, this is the start. Then the next thing we do is actually solve for dy dx. We subtract the things that don't have a dy dx. So I'll subtract the 2x, I'll add the 2y. Then of the remaining terms that have the dy dx, I can factor it out. It's just, something that's being multiplied. So we can factor. So after I factor dy dx out, I'm going to be able to divide by negative 2x plus 2y. I end up with something that ends up being 1 in this situation. Let's just change the number, that way it doesn't happen like this. Let's turn this to a 3. 3. That stays as 2, that stays as 2. This is 3, this is 3. This is 3, this is 3. Okay. So 2x plus 3y over negative 3x plus 2y. Okay, now if we had a point that worked in here, we'd plug that point into here to find the tangent slope. Okay, it has to be a point, x's and y's. But be careful with second derivatives. Like say we are given dy dx is equal to xy cubed. If I were to take the derivative of this with respect to x, I would get that d squared y over dx squared. That's where it comes from. But derivative of xy cubed would be the derivative of the first times the second plus the derivative of the second, 3y squared, dy dx times the first. Now, typically we will be asked to find a second derivative in terms of x and y, which means we can't leave dy dx. But don't worry, we know what dy dx is equal to, so we could plug it in there. I get d squared y over dx squared equals y cubed plus 3y squared times xy cubed times x. And we can do a lot of simplification if we wanted to. I'm just going to leave it like that. Okay, so second derivatives, make sure we plug back in for dy dx. If you're given dy dx and you ask for horizontal and vertical tangents, remember a horizontal tangent occurs when our derivative is 0. So that means 0 divided by any number. So for this situation, if this is dy dx, I would just set 3 minus x equal to 0, and I get x equals 3. Be able to find what the y is by plugging it back into our original equation. Vertical tangents are when dy dx has a 0 in the denominator. If we have a number over 0, an undefined tangent slope, that would be a location of a vertical tangent. Well, in this situation, and this is just an example, it's not like always going to be like this. If you end up with a equation equal to 0, you can't necessarily find a value. But you can solve for a variable, and what you would do is you would take this, you'd plug it back into your original equation to then find your points. So I would take like 2x and replace the original equation, wherever y was, I would replace it with 2x. Be able to solve for that. Related rates is all about finding how things changed at a specific moment in time. So instead of taking derivatives with respect to x, all of a sudden we're taking derivatives, not necessarily of just random functions, but just equations that tell us about things going on in the world, like volumes of spheres the change in the volume of the sphere would be equal to 4 pi r squared times the change in the radius. Here, Pythagorean theorem used for distances, I would have 2x dx dt, so the change in my x distance plus 2y times dy dt equals 2d times dd dt. Be able to cancel those 2's there. Okay. Keys with related rates is to plug in fixed values before taking derivatives. Here's like a cone problem. Say we have water being poured into this cone, and we're trying to figure out how quickly the height of the water is changing. Well, like, you don't want to take the derivative of this because you have 3 variables and you'd have to use the product rule. But because of the proportionality of the height and the radius of the tank to the height and the radius of the water, we could create a proportion, and that's always going to be fixed, where the radius and the height of the water will be proportional to the radius and the height of the tank. Let's say we're trying to find out how quickly the height of the tank is changing. I'd be able to solve for R. That can get plugged into this formula, giving us V equals 1/3 pi times 1/3 h squared h. Before taking the derivative, I would simplify this. This turns into 1/9 h squared, but the h squared can be multiplied by this h to be h cubed. Now I'm ready to take the derivative of this with respect to t. This is just one example of plugging in something that is fixed. dv dt would equal pi times 1/9 h squared times dh dt. You'd be able to plug in that information. Example like this, if a guy's watching the space shuttle launch and the guy is constantly 400 yards away from the launch pad, we can actually just plug in 400 in for x and not have to worry about x because it ends up dx dt is 0. There's no change in x. You'd then be able to take the derivative of this with respect to t and kind of go from there, plug in your other information. Okay, so that's related rates. It's just taking derivatives with respect to t, using the derivative rules, but with a d blank dt after each derivative. So that really is all of Unit 5, these implicit derivatives and related rates problems. There's just lots of different types of problems, which is why we spent 2 days on related rates problems and 2 days on these new implicit derivatives. All right? Great.